get started. Thank you all for coming. We have 3 wonderful sessions planned today. Just a few quick announcements. So we meet third Wednesday of every month. So next one's on October 17. We do post the slides and video at the locations you see here. And again, you know, we've been pretty good about this, but if you need to talk, we request you to move back to the room so that others don't get disturbed. Speakers and suggestions, we're always looking for topics, speakers, so if you have ideas that you want to present, please. Let me welcome Konstantin Shvachko. Konstantin's a veteran Hadoop developer, is also the founder of AltoScale. He specializes in efficient data structures and algorithms for large-scale distributed computing. He holds a PhD in computer science from the University of Moscow, Russia. He's also a member of the Apache Hadoop PMC. Welcome, Konstantin.
Thank you for the introduction. You hear me well? So I should apologize first of all about the confusion about the company name. I want to forget to change the name into a different name due to business decisions. So we're now AltoStorage Technologies, AltoStorage in short, and this is pretty close to what it was before. And as before, we're dedicated to Hadoop and cloud technology. So I'll be talking about Giraffa today, and I'm glad to start this session. I think that Giraffa and Sergey will be covering some African motifs, and we'll have a drill in the middle. So Giraffa is a distributed, highly available file system. It is built from HDFS DataNodes component, and it is a new open source project in very experimental stage, so don't use it in production yet. Apache Hadoop, as we know, it is a distributed storage and computing system. It consists of the storage layer, distributed file system, and computational framework, MapReduce. It is also a data system of data tools. I will mention only HBase and Zookeeper today because they have direct relation to what we're building today. Design principles are important for Hadoop. The first of them being linear scalability. Linear scalability is almost in storage and computation. Reliability and availability is important design principle because Hadoop cluster runs on thousands of nodes, and some nodes will be failing every day. Moving computation to data minimizes expensive data transfer, and sequential data processing avoids random reads. If you need to use lots of random reads, then you use other systems, HBase being one of them. If you look at Hadoop cluster, it's a symbiosis of interleaving storage and computational clusters, and that basically what provides local execution of data, because tasks run on data location. If we look at the bottom part of the picture, we see that slave nodes running constructors and data nodes are distributed. It is a distributed system that conforms to the principles, the design principles put into including scalability, availability, and reliability. But the top level are single nodes, single master nodes, which are main node for HDFS and job driver for marketing. HDFS is, from user point perspective, is a regular file system with files and directories, but with people. Namespace, the entire metadata decoupled from data in HDFS, and it is stored in a single data node that accelerates substantially metadata operations, which usually are short, and there's lots of them, and separates them from, decoupling them from long heavy data transfer. And data nodes store blocks, block represents as local files of data nodes. Blocks are replicated by default data types, and this is done both for redundancy and availability. So HDFS client is sort of an entry point for HDFS, and it glues together different components so that they can work together. Single master architecture, as we have seen, is a scalability limit for these days. And I will mention the scalability limits. First of them, that a single master becomes a performance bottleneck. A handful of loopback clients can saturate main node performance. We have seen batch jobs, not very big, 200 numbers, can access the same non-existing file in HDFS, and that will bring the cluster as a service, make the cluster service unusable. There are other examples. For example, you can run TFS test on your cluster with 1,000 numbers, creating lots of small files, and your name node will become unresponsive. Single point of failure also relates to, first of all, availability, because if the name node goes down, then the whole cluster is not available. And last but not least, the space limit is limited by a single name node. Design every object with the name node is stored in RAM. Since it occupies a specific number of bytes, there is a limit to the number of objects on the name node, which reduces the limit of the number of blocks that the file system can handle, and that in turn limits the capacity of the whole cluster. More details will be found in my Unix blogging article published a couple years ago for blog respect. This diagram visualizes the evolution of node count on the cluster. So we see that in several years, the node count went down to 2,000 nodes. This is reflected with these clusters actually have the same computational and storage effect, and the streaming happens because the vertical growth of the servers themselves. So they can do, they're kind of denser and can have more memory and better performance. And we can estimate that the clusters will shrink into 500 nodes. With 500 nodes is not such a big, doesn't look like such a big cluster, and it's probably will be affordable for many companies to hit the scalability limit, not only the big guys like companies listed there. And if we take it with perspective that information is growing exponentially, we come to the conclusion that we either need to do something or run multiple instances, multiple clusters in our data centers in order to process and store all that information. Or Hadoop version 2 has current Hadoop version 1 is stable release. Going to Hadoop 2, we have pretty good scalability storage. First of all, federation is coming in. Federation is an approach to run multiple independent name nodes, sharing a common pool of data nodes. This systems, and there is UFS, which is a client-side model, which joins those volumes together or to represent them in a consistent way to the client or different client. I'm mentioning Yahoo here because this is the market use scalability story, and I'm mentioning because if the computation framework scales higher than the storage layer should follow the trend. So the question is, what's beyond Hadoop version 2, and how to target, how to tackle scalability problems there. And we think that the system that is based on the principle of the namespace partitioning is the answer to that. So federation is a static partitioning. You have multiple independent name nodes. It happens that on your installation, one name node grows faster than others. They all the resources themselves, and it's the same limitation as single name. Within any partitioning, these resources will be equally distributed between different nodes. Giraffa is built from HDFS and HBase endpoints. This will accelerate the development process for Giraffa because many problems that need to be addressed in the new file system are already addressed in those two points. So Giraffa will store file directory metadata on HBase table. HBase table is a big sparse table. I'll have an overview of HBase later. So it also dynamically partitions this table into regions and provides distributed cache because it stores all the information, it caches all the information in memory. The data itself will be stored exactly the same as it is in HDFS or DataNodes as data logs, and streaming and pipelining of data will change. There is a middle layer between those two, which is called log management. This layer will handle communication with data nodes like HBase and log reports, and will perform internal cluster maintenance like log replication, inflation, and also responsible for allocation. There are three main motivations for Giraffa. Availability is the primary goal, and they're basically sort of in the order of importance. And load balancing of metadata traffic is one of the main issues that Giraffa is addressing. Same data stream speed, not changing that, and continuous availability. Continuous availability is a term introduced by my colleague at AltoScale. So this is to distinguish availability, continuous availability from high availability. From high availability, we have two synchronous nodes that are that keep the state in sync and are ready to, when any of them is ready to take over if the other payment. So continuous availability. There is no such application of state. It's like with data, one data node goes down over here because the work that they will be distributed with are the same thing with the cluster of with a cluster that serves metadata. Cluster availability is another important issue. We want to operate a bigger cluster as a single unit, because otherwise multiple clusters would require multiple of operation effort. And more files and more data, of course, is an important goal. And these are the numbers for comparison of where we are and what we're like. A few words about HBase. HBase is a distributed metadata store. It presents data as data sparsely structured tables. Table is a collection of rows. The table is sorted by row keys. Rows can have a particular number of columns. HBase provides dynamic table positioning. It partitions tables horizontally in regions, and regions are assigned to region servers, loaded into memory and served from the region servers to high-level application. In that sense, HBase can be considered as a distributed cache. And that's why it's more real-time consistent implementation. So this is a pretty convoluted diagram with lots of implementation details. For us, it's important to see that there are region servers, multiple region servers in HBase. The region servers store regions, and regions are stored in a reliable distributed file system. HDFS, in our case, has files in that. An HBase API can be split into three main categories. First, the administration functions that are responsible for table management, creation, deletion, some internal housekeeping, like splitting regions and compacting. The access to data goes through get and put operations, get, put, delete. There is a scanner that provides you a stream of rows, and you can use a variety of filters in HBase to control what is streamed to those scanners. Call processor is a relatively new thing in HBase, and it allows people to insert some custom actions into the HBase, which are executed on the server. And those custom actions are very important for building Giraffa, and they're similar to database triggers or storage. There are 4 building blocks for Giraffa. Giraffa client fetches metadata from namespace service and streams data from or to a node. The namespace service is basically a big table with rows. Each row represents a file or a directory, and it contains all the metadata of file system object. Block management is, as I said, an equal layer between namespace and data management data nodes. It's a distributed collection of block metadata. Data management is just data. So this is the high-level architecture of Giraffa applications using Giraffa client, which we call namespace agent, connect with namespace service, relock, and get metadata information, and using that metadata information to access data. There is a block management layer which is in the middle, and all the block operations are triggered by the namespace service and served by the block management layer. This is a closer look into Giraffa client. HDFS has a common interface called file system. So Giraffa implements the file system interface in order to instantiate this file. You just need to specify this two configuration parameters, and you will use Giraffa instead of HDFS. Giraffa file system directly refers to Giraffa client, and Giraffa client is an extension of DFS client. DFS client is a standard module in HDFS that processes communication between name nodes and data nodes. And in this module Giraffa client replaces the RPC connector to the name node with namespace agent. And namespace agent addresses to the two HBase as if it's the name node. So GFS client doesn't need to be changed and receives exactly the same data as it was received from the name node. And it can use that data to connect the table node. And that code path is completely unchanged. Namespace table is in the namespace service, the whole file system is represented by a table called namespace. So row keys play file IDs, they identify files. The row also contains all the file attributes of the HDFS files, or Giraffa files. It contains a list of blocks, which is persisted in the table, and it contains a list of block locations, which are not persisted in the table, they are just a cache of that information is obtained from the block manager during startup. It is populated into the namespace table. And directories have an additional structure called directory table, which maps directory entry names into row keys of those entries. A closer look is zoomed into HBase namespace service. So we see regions here, and we see region servers here, and we see regions serving by those region servers. There are two things that we added to Giraffa adds to region server. The two call processors. The first one is namespace processor, which processes all the requests coming from client. And there is one management processor that triggers block allocation request to the block management layer. And the block manager basically maintains a flat namespace of blocks. It's easy to distribute the flat namespace. It serves three main functions. As that block management, is block allocation, deletion, replication. It also maintains data nodes, processes their revolving course RDs, and detects failed data nodes. And the third one is that it provides a storage for HBase files. In order to store the table HBase in HDFS, and block manager will play that role in Giraffa design. When we run the cluster, the block manager servers, individual servers, will run on the region servers, and that will make all access to most of the access to the block manager from region servers locally. And we choose name node as an initial implementation of block manager servers. In the future, we will have to see all the complexities, many of the complexities of the name node for the block manager. Data management is just data node. So data transfer, data pipeline are exactly the same as HDFS. Row key design is one of the most important issues that Giraffa is facing. In addition to identifying files in the table, row key also defines sorting of the rows in the table. And by defining sorting of the row, it defines partitioning of the rows, because they are partitioned horizontally based on in the order they are stored in the table. So in Giraffa, we would like to experiment with different key definitions depending on locality requirements. And key definitions should be chosen at the time of formatting your file system. You do not change it on the fly. At least that's the key. Default implementation full path key And this is not a very satisfactory definition of the key, because a single domain, even name the local file name, can move the file into a different region, and that makes it non-atomic, and we want to avoid that. In order to avoid that, we will need to introduce inode numbers and base row keys on the inode number. So what's the locality requirement? We want the objects of the same directory to be adjacent in the table. So basically, when we look at the transition from the tree structure that the file system is into the table, this is a linearization of the tree. We're projecting the hierarchical tree structure into a linear array represented by ordered records of the table. And this projection can be done in many different ways. The requirement that we are putting in this projection that adjacent objects in the tree should be adjacent most of the time into the structure. And there is lots of different ways to do that. I'm giving 3 examples here. This is and have a locality presentation of projection of the hierarchy into the table. So in the bottom, you can consider it as a table, and on top is the file system tree. So if we hash, then projection is random, and does not guarantee that objects from the same directory will go into the same object. This is what gives us current default implementation of full path. Basically, we are projecting full subtree into the same region. This is a good partitioning, because it guarantees locality, but it may be better than we need. What we need, we don't need to all the ancestors of the same node to go into the same line. We don't need to keep them close. We just need the closest relatives, sort of forming a community, unbreakable community that will be transferred if needed to move between regions. So this is a fixed neighborhood partitioning that serves the I'll stop for a moment on atomic renaming, because it's an important problem generally in distributed computing. So we plan to implement atomic in place, what we call rename, which is changing the local name of the file. But we will not implement, in short, we will not support the move of the file which is standard POSIX rename. Instead of that, the move can be handled on the application layer, and there is a simple procedure. As an example, that we see that I showed here a simple procedure that you move the file from the stored directory to the temporary name in the target directory, and then rename the temporary file to the original name, or to the site name. And this procedure is not atomic, it can fail in the middle, but there is a simple three-step procedure on the next line that can reach propagation and recover from failure. Eventually, there is of course possibility to implement atomic moves with access or simplified synchronization logging like that. This is super. So three-step procedure. I was talking mostly till now about how Giraffa will cover functionality of HDFS. But Giraffa also also will provide a new functionality. I'll give two examples. First is custom file attribute. This is user-defined metadata for files in the directory. Right now, if you need to introduce that, and the application programs know that very well, they either encode it into a complex file name